Hello, my name is Wyatt Clausen, and today I am presenting flood prediction using machine learning. The paper was written by Abdalla Alamen and myself, and I'm presenting from Minnesota State University, Mankato. So, our problem here is that floods are among the most frequent and destructive natural disasters. They cause loss of life, property damage, and economic disruption. Because of this, our goal is to leverage machine learning techniques to build accurate, scalable, and cost-effective flood prediction systems. So before we worked on our project here, we first reviewed prior machine learning models that were used, such as decision trees, artificial neural networks, convolutional neural networks, logistic regressions, support vector machines, long short-term memory, ensemble learning, ONFIS, wavelet neural networks, inundation models, and also gradient boosting models. So for our project, we use two different data sets. The first data set comes from the Bangladesh government. It contains over 20,000 records, and 18 variables associated with meteorology and geography. And it spans from 1949 to 2014. On the other hand, we have data collected from the Minnesota River. To be specific, it's a time series data set of gauge height for the Minnesota River in feet, and it spans from 2019 to 2025. Here is the visual representation of our Minnesota River data. Here we can see the gauge height in feet, as well as points of minor flooding, moderate flooding, and major flooding, as we see on this graph. So we have it appears we have a bit of a seasonal pattern here. It occurs in like the spring and summer. Next, for the Bangladesh data set, here were the final variables that we chose for our model. We have a categorical and numerical variables. We have station name, year, month, maximum and minimum temperature in Celsius, rainfall in centimeters, relative humidity in percentage, wind speed in meters per second, cloud coverage in octa, the number of hours per day for bright sunshine, the x coordinate, the y coordinate, altitude in meters, and our dependent variable, flood, is a binary variable, where one is yes, and the null is considered no flood. So for the class distribution of our Bangladesh data, we have over 16,000 non-flood observations and 4,000 flood observations. Because of this, there's going to be a moderate imbalance in our data set, which will bias the model into predicting zero. Because of this, we require more evaluation metrics beyond accuracy, because accuracy alone can be misleading in imbalanced data sets. So we rely on precision, recall, F1, error metrics, and hydrological efficiency metrics. So for pre-processing the data, first we clean the data by replacing null values with zeros in the flood feature, since there are no other null values in either of the two data sets. Second, we use the label encoder to encode our categorical data. For feature scaling, we used the min-max scaler for Minnesota data and a standard scaler for Bangladesh data. For splitting the data into training and testing data sets, we used an 80-20%, so 80% for training data, 20% for testing data, which led to our final sample size for the Bangladesh data set to be over 16,000 for the training set and 4,000 and over 4,000 for the test data set. And then for the Minnesota River time series data set, we calculated the daily average for gauge height, since it was recorded every 15 minutes per day. So we have the five main machine learning models that we used with our data sets. We used long short-term memory, since it was good for time series forecasting and captured temporal flood patterns. We used LightGBM, a gradient boosting model, as it handles tabular data efficiently and captures complex feature interactions. We used support vector machines, which is effective for classification of flood versus no flood scenarios with high precision. We used a multilayer perceptron, which learns nonlinear relationships between multiple flood-related factors. And finally, we used random forests, since it reduces overfitting and works well on mixed datasets. In addition, we used a variety of performance metrics to study the efficiency of our machine learning models. First, we used the basic ones. We used accuracy, precision, recall, and F1 score to evaluate the classification quality of flood versus no flood prediction. Second, we used mean square error and regular mean square error to measure the prediction error for continuous values, like water level. Next, we used a confusion matrix to give a detailed breakdown of correct versus incorrect classifications. Finally, we used two major hydrology metrics used in hydrology, NSE and KGE, which are Nash-Sutcliffe Efficiency and Kling-Gupta Efficiency effectively, which study predictions versus observations, as well as correlation, respectively. So for the Minnesota River, we used long short-term memory and LightGBM. First, with the long short-term memory, we have a RIP MSE of 0.017 and a KGE and NSE of 0.993. For the LightGBM, we had a RIP MSE of 0.037 and a KGE of 0.937 and an NSE of 0.957. Since it appears that long short-term memory has the lower RIP MSE and higher KGE and NSE values, it was better for this data set than the LightGBM. As for the Bangladesh data findings, we found out that LightGBM could be considered the best out of the 5 models, since it had the highest accuracy, precision, recall, F1 score, NSE and KGE values, as well as having the lowest MSE and RIP MSE values. While the other models also performed very well, having their performance metrics be almost in like the 80s and 90s. To give us a detailed breakdown of our classifications, we used our confusion matrices. As we can see here, almost all of the confusion matrices, almost all of the machine learning models were biased towards predicting 0 due to our imbalanced data set. However, the only ones that weren't biased towards 0 were the LightGBM, which predicted equal false negatives and false positives, as well as the multilayer perceptron, which predicted more false positives than false negatives. Other than that, it appears that all of the other machine learning models are biased towards predicting false negatives. Here is a visual comparison of our performance metrics. More specifically, root mean square error, NSE, KGE, as well as accuracy. This also confirms that the LightGBM model appeared to perform the best out of the 5, due to having the highest NSE and KGE, the highest accuracy, as well as the lowest root mean square error. In addition, we used an ROC curve to show that all models have achieved excellent discrimination between flood and non-flood events, reaching near perfect separability, with random forest here actually yielding the highest area under the curve value of 0.996. However, all of the other ones have also achieved AUC scores of over 0.9. Since LightGBM was our best performing model, we decided to review the feature importance of this model. Here it showed that rainfall was is the most important feature, followed by station name, the X and Y coordinates, and the year. However, it's important to note that station name and X and Y coordinate could have could have high coral could have high autocorrelation, which could skew results. So for the key findings, first, LightGBM performs the best due to handling of mixed feature types, as it works well with both numerical and categorical features. It has strong regularization techniques to prevent overfitting, making the model generalize well. In addition, it is able to capture nonlinear interactions. As flooding is influenced by multiple interacting variables, LightGBM automatically handles this. In addition, the random forest is also strong and stable, as it handles noise, outliers, and nonlinearities. However, neural network models will need more sequential or larger datasets. For example, our Bangladesh dataset is not is not a true continuous time series, since it was recorded station by station. So essentially, it's a combination of multiple time series datasets, which limited the effectiveness of the long short-term memory model. So for future research, we would like to collect more Minnesota data. Since we only studied gauge height, we should probably collect more value observations, such as rainfall or temperature. We can utilize hybridization techniques. For example, we can create a hybridization of a CNN with a long short-term memory, where the CNN extracts spatial features, while the LSTM learns time patterns, resulting in a stronger combined model. Next, we can integrate satellites, soil moisture, river level, and topographic data, which provides real physical drivers of floods, like upstream rainfall or ground saturation. Fourth, we can add GIS spatial modeling. We can use geographic software to analyze flood risk geographically using maps, elevation, water flow, and spatial patterns. And finally, we could develop a real-time forecasting model using continuously updated weather data for early warning systems. So in conclusion, the LightGBM model achieved the best overall performance. Machine learning techniques show strong potential for supporting early warning systems. And finally, further data enhancements can significantly improve model accuracy. Here are my sources for the literature review. And thank you for watching. Do you have any questions?